4. Invoking Lambda functions. Each event source invokes a Lambda function by using either a push or a pull model. In the push model, an event source directly invokes the Lambda function when the event occurs. In the pull or polling model, an event source puts information into a stream or queue. Lambda pulls the stream or queue and invokes your function when it detects an event. What are the types of push events? For synchronous invocation, the other service waits for your function's response. Consider an example where API Gateway is the event source. In this case, when a client makes a request to your API, that client expects a response immediately. This model has no built-in retry in Lambda. You must manage your retry strategy in your application code. Examples of synchronous event sources include Elastic Load Balancing, Amazon Cognito, Amazon Lex, Amazon Alexa, API Gateway, AWS CloudFormation, Amazon CloudFront, and Amazon Kinesis Data Firehose. For asynchronous invocation, Lambda queues the event before passing it to your function. The other service gets a success response as soon as the event is queued and isn't aware of what happens afterwards. The event source sends it, then forgets it. If an error occurs, Lambda will automatically retry the invocation twice. It can send failed events to a dead letter queue that you configure. Examples of asynchronous event sources include Amazon Simple Storage Service, also called Amazon S3, Amazon Simple Notification Service, known as Amazon SNS, Amazon Simple Email Service, also called Amazon SES, CloudFormation, CloudWatch Logs, CloudWatch Events, AWS Code Commit, and AWS Config. In both cases, you invoke your Lambda function by using the invoke operation, and you can specify the invocation type as synchronous or asynchronous. When using an AWS service as trigger, the invocation type is predetermined for each service. You don't have control over the invocation type that these event sources use. In the polling model, Lambda uses event source mappings to get information from a stream or queue. Lambda polls the stream or queue. If it finds records, it delivers the payload and invokes the Lambda function. In this model, the Lambda service itself extracts data from the stream or queue for the Lambda function to process. Stream-based event sources include DynamoDB streams and Amazon Kinesis data streams. Stream records are organized into shards. Lambda pulls the stream for records and attempts to invoke the function. If a failure occurs, Lambda won't read any new shards until the failed batch expires or is processed successfully. You can configure error handling options to modify how Lambda deals with errors. Queue-based event sources include Amazon Simple Queue Service or Amazon SQS. Lambda pulls the queue for records. If the invocation fails or times out, then the failed message is returned to the queue. Lambda continues to retry the failed message until it's processed successfully, or the retry limit or message retention period is reached. Failed messages can be sent to an on-failure destination or a dead letter queue. Polling doesn't incur a charge. You are charged only if actions result from a poll. With streams, Lambda retries a failed record until it succeeds or reaches a 24-hour expiration. Thus, a failing record can block processing. You can configure error handling options to bypass failing records and send them to an on-failure destination for offline processing. With queues, failed records become visible on the queue to be resent to your Lambda function up to a number of retries which you can configure. You can send records that continue to fail to a dead letter queue. This example shows the command line code to invoke a function synchronously and illustrates the format of the response from Lambda. Notice that with a synchronous event, the acknowledgement is the 200 status. This example shows the command line code to invoke a function asynchronously and illustrates the format of the response from Lambda. Notice that with an asynchronous event, the acknowledgement is the 202 status, which indicates that the request was received. Here are the key takeaways for this section of the module. Lambda invokes Lambda functions by using the synchronous, asynchronous, or polling invocation model. Polling is also known as event source mapping. Lambda has built-in handling that differs by event source type. Thanks for watching. We'll see you in the next video. This video covers Section 5, Setting Permissions for Lambda. Lambda requires two types of permissions. First, event sources need permissions to invoke a Lambda function. Next, Lambda functions need permissions to interact with other AWS services and resources. Permissions are handled through IAM. An IAM resource policy tells the Lambda service which push event sources have permissions to invoke the Lambda function. Resource policies also make it easy to grant access to the Lambda function across AWS accounts. For example, suppose that you need an S3 bucket in account A to invoke your Lambda function in account B. You can create a resource policy that allows account A to invoke the function in account B. Notice that the IAM resource policy is on the bucket, not on the Lambda function. In this example, the resource policy on an S3 bucket gives Amazon S3 permissions to invoke the Lambda function called myFirstFunction. The Lambda execution role grants your Lambda function permissions to access AWS services and resources. You select or create the execution role when you create the function. Two policies are attached to the execution role. The first is the IAM policy. This policy defines the actions that the Lambda function can take on another AWS service or resource, such as writing to a DynamoDB table. The second is the trust policy, which allows the Lambda service to assume the execution role. To grant permissions to Lambda to use the assume role action, you must have permissions for the IAM pass role action. Polling event sources also need the execution role to give the Lambda function permissions to read from the queue or stream. The Lambda function also needs the execution role to poll event sources to be able to read from the queue or stream. IAM policies are associated with a role that another entity, such as Lambda or another resource, can assume. Policies aren't directly attached to a Lambda function. The IAM policy example here allows the Lambda function to perform some CloudWatch logs actions. These actions include creating a log group and log stream and writing to the log stream. The trust policy example gives the Lambda service permissions to assume the role and invoke the Lambda function on your behalf. This example shows code for the AWS command line interface, or AWS CLI. This code gives Amazon SNS permissions to invoke a function and shows the IAM policy statement that results. Here are the key takeaways for this section of the module. Lambda functions require permissions to be invoked and permissions to interact with other services. Both types of permissions are defined by using IAM or trust policies. Thanks for watching. We'll see you in the next video. Authoring and configuring Lambda functions. When you create a Lambda function, you specify the function handler. The Lambda function handler is the entry point that Lambda calls to start running your Lambda function. The handler method always takes two objects, the event object and the context object. The event object provides information about the event that invoked the Lambda function. This information could be a predefined object that an AWS service generates, or it could be a custom user-defined object. A user-defined object could be a serializable string, such as plain old Java object, also called POJO, or a JSON stream. The contents of the event object include all the data and metadata that your Lambda function needs to drive its logic. The contents and structure of the event object vary, depending on which event source created it. For example, an event that API Gateway creates might contain details that are related to the HTTPS request that the API client made. The details might include path, query string, and request body. However, an event that Amazon S3 creates would include details about the bucket and the new object. The context object is where AWS generates a context object and provides runtime information. The context object enables your function code to interact with the Lambda runtime environment. The contents and structure of the context object vary based on the language runtime that your Lambda function uses. At a minimum, the context object will contain three methods or properties. The first is the AWS request ID. This property is used to track specific invocations of a Lambda function. This is important for error reporting or when contacting AWS support. The second item is the log stream name. This is the CloudWatch log stream that your log statements will be sent to. The final item is the getRemainingTime in millis method. This method returns the number of milliseconds that remain before running your function times out. This is an example of a Lambda function that is written in Python. It defines a handler function that is called lambda_handler. The function returns a message that contains data from the event that it received as input. Notice that each language has its own requirements for how a function handler can be defined and referenced within the deployment package. This slide shows what the example from the previous slide looks like if you write and test it by using the Lambda console. Memory and timeout are configurations that determine how your Lambda function performs. These configurations affect your billing. With Lambda, you are charged based on the total number of requests across all your functions. You are also charged based on the duration, meaning the time it takes for your code to run. The price depends on the amount of memory that you allocate to your function. Memory refers to the amount of memory you specify that you want to allocate to your Lambda function. Lambda then allocates CPU power that is proportional to the memory. Lambda is priced so that the cost per 1 millisecond of function duration increases as the memory configuration increases. The timeout configuration allows you to control the maximum duration of your function. Using a timeout can prevent higher costs that come from long-running functions. You must find the right balance between not letting the function run too long and being able to finish under normal circumstances. One best practice is to test the performance of your Lambda function to make sure that you choose the optimum memory size configuration. You can view the memory usage for your function in Cloud Watch Logs. Another best practice is to load test your Lambda function to analyze how long it runs and determine the best timeout value. This information is important when your Lambda function makes network calls to resources that might not be able to handle the scaling of Lambda functions. Lambda offers several resource-related configurations, such as how Lambda interacts with other AWS resources to adapt to different use cases. For example, you might need to connect to a private cloud or VPC, an Amazon Relational Database Service, also called Amazon RDS, instance, or an Amazon Elastic File System, also called Amazon EFS file system. You can also configure details that are related to event sources, such as destinations, and asynchronous invocation details. Both types are relevant to asynchronous event sources. Destinations can also be used for streaming event sources. You can also configure AWS step function state machines that can directly invoke your function in one of their steps. Code-related configurations are also available. These include the runtime that the function will use or language that the code will be written in. You can specify environment variables, which are key value pairs that are accessible from your function code. You can configure tags, which are labels you assign to an AWS resource. Each tag consists of a key and an option value. And you can use code signing, which ensures that the code has been signed by an approved source and has not been altered. There are a few best practices to follow when you design your Lambda function. First, treat functions as stateless. Don't save any information about state within the context of the function itself, because your functions exist only when your work must be done. It's important for serverless applications to treat each function as stateless. Second, include only what you need. Minimize both the size and the dependencies of your deployment package to reduce the startup time for your function. For example, choose only the modules that you need, such as the DynamoDB and Amazon S3 SDK modules and the Lambda core libraries. Don't include an entire AWS SDK library in your deployment package. Along with this, reduce the time that it takes Lambda to unpack deployment packages that are authored in Java. And minimize the complexity of your dependencies. Choose simpler Java dependency injection frameworks. For example, choose Dagger or Juice instead of more complex frameworks like Spring. The last best practice is to reuse the temporary runtime environment to improve function performance. This environment initializes any external dependencies of your Lambda function code. Make sure that any externalized configuration or dependencies that your code retrieves are stored and referenced locally after the initial run. Limit reinitializing variables and objects on every invocation. Keep alive and reuse connections such as HTTP, database, or others that were established during a previous invocation. There are also best practices for writing code. First, separate the core business logic from the handler method. This makes your code more portable, and you can target unit tests at your code without concern about the function configuration. The second best practice is to write modular functions. Create single-purpose functions. Third, include logging statements. Lambda functions can and should include logging statements that are written to CloudWatch. The fourth best practice is to include results information. Functions must give information to Lambda about the results of their run. Next, use environment variables. With environment variables, you can pass operational parameters and configuration settings to your function without making changes to the code itself. For example, if you are writing to an S3 bucket, configure the bucket name as an environment variable instead of hard-coding the bucket name. You can also use environment variables to store sensitive information that the function requires. Another best practice is to avoid using recursive code. Avoid a situation where a function calls itself. In this circumstance, it might continue to spawn new invocations that would cause you to lose control of your concurrency. And finally, don't call one function from another. Instead, use destinations or orchestrate with step functions. Higher memory configurations have a higher per 1 millisecond cost, but might decrease duration costs and concurrency needs. For example, with applications that are CPU intensive, increasing the memory, which provides more CPU, can shorten the duration of the function. Therefore, it might be cheaper to run it at the higher memory level. Use the power tuning utility to find the balance that suits your application needs. Here are the key takeaways for this section of the module. Lambda supports different languages and runtimes. The function handler is the entry point into the Lambda function. You can configure attributes, including the amount of memory and function timeout. Follow best coding practices to create efficient Lambda functions. Thanks for watching. We'll see you in the next video. This video covers Section 7, Deploying Lambda Functions. To deploy a Lambda function with the Lambda API, command line tools, or the AWS SDKs, you must create a Lambda function deployment package. You also must create a deployment package if your function uses a compiled language or to add dependencies to your function. You can create two types of deployment packages, .zip archives or container images. If you use a .zip archive, choose a runtime when you use the Lambda console or a toolkit to create a function. When you author your function, Lambda will automatically create the .zip file of your code. You can also use the container image for your deployment package. It is possible to use familiar container tooling, workflows, or dependencies to build applications that are based on Lambda. You can use the console or integrated development environment, also called an IDE, to author Lambda functions. For .zip file deployment packages, you have three options for providing the deployment package to the Lambda service. The first is the Lambda console editor. If your code does not require custom libraries other than the AWS SDK, then you can edit your code inline through the console. The console compresses your code with the relevant configuration information into a deployment package that the Lambda service can run. This deployment choice is ideal for simple scenarios. The second option is to upload the deployment package directly from your IDE. In most scenarios where your code requires custom libraries, you can create your deployment package in your IDE. Then you can upload it through the Lambda console. The third option is to compress and upload to an S3 bucket and provide the S3 bucket, object key, and optional version for the object. Lambda will load your code directly from Amazon S3. The deployment packages have the following limits: 50 megabytes for compressed and direct upload, 250 megabytes for not compressed, including layers, 3 megabytes when using the console editor, and 512 kilobytes maximum for an individual file. When you deploy a container image, first deploy the image to the Amazon Elastic Container Registry Service, also known as Amazon ECR, by using the Docker push command. During the Lambda create or update process, the Lambda service pulls the image from Amazon ECR, optimizes the image for use, and deploys the image to the Lambda service. After this process, any other configuration processes are complete. The Lambda function is then in active status and ready to be invoked. Versions are immutable copies of the code and configuration of your Lambda function. Use versioning to publish one or more versions of your function. As a result, you can work with different variations of your Lambda function in your development workflow, such as development, beta, and production. When you create a Lambda function, only one version exists, the $latest version. You can refer to this function by using its Amazon resource name, or ARN. When you publish a new version, Lambda makes a snapshot copy of the $latest version to create the new one. The new version has a unique ARN that includes a new sequential version number. You can create aliases for your Lambda function. Conceptually, an alias is a pointer to a specific Lambda function version. Use the alias in the ARN to reference the Lambda function version that is currently associated with that alias. Using an alias makes it easy to promote or roll back versions without changing any code. Aliases abstract the need to know which version is being referenced. In this example, the test alias points to version 2 of the Lambda function. Suppose that Amazon S3 is the event source that invokes your Lambda function when new objects are created in a bucket. When S3 is your event source, you store the information for event source mapping in the configuration for bucket notifications. In that configuration, you can identify the Lambda function ARN that S3 can invoke. However, in this case, you must update the notification configuration. This is necessary so that S3 will invoke the correct version each time you publish a new version of your Lambda function. Instead of specifying the function ARN, you can specify an alias ARN in the notification configuration. For example, you can specify the prod alias ARN. As you promote new versions of your Lambda function into production, you only must update the prod alias to point to the latest stable version. You don't need to update the notification configuration in S3. With custom runtimes, you can use other languages in Lambda. The Lambda execution environment provides a runtime interface to get events and send responses. The bootstrap file is the runtime's entry point, and you can deploy a custom runtime next to your function code or in a layer. Even when using a standard runtime, when you build serverless applications, it's common to have code shared across Lambda functions. It can be custom code that more than one function uses, or a standard library that you add to simplify the implementation of your business logic. Previously, you needed to package and deploy the shared code together with all of the functions that used it. Now you can configure your Lambda function to include additional code and content as layers. A layer is a .zip archive that contains libraries, a custom runtime, or other dependencies. With layers, you can use libraries in your function without needing to include them in your deployment package. It's a best practice to have smaller deployment packages and to share common dependencies with layers. You can use layers to keep your deployment package small, which makes development easier. You can avoid errors that can occur when you install and package dependencies with your function code. For Node.js, Python, and Ruby functions, if you keep your deployment package under 3 megabytes, you can develop your function code in the Lambda console. A function can use up to 5 layers at a time. The total extracted size of the function at all layers cannot exceed the extracted deployment package size limit of 250 megabytes. The code snippets here illustrate how you would use the AWS CLI to deploy a function. These code snippets illustrate how you would update an existing function by using the AWS CLI. Here are the key takeaways for this section of the module. Lambda has built-in versioning so that you can create immutable versions of your code. You can use aliases to point at different versions of your Lambda function. Lambda provides popular runtimes, but you can create custom runtimes. Lambda layers are libraries of code that you create and which other Lambda functions can call. Thanks for watching. We'll see you in the next video. This video covers Section 8, Monitoring and Debugging Tools for Application Developers. With modern applications, and particularly with serverless ones, you must deal with short-lived resources. You also encounter many different services that are connected in a distributed way and faster release velocity of independent components. The user experience has also become a more important consideration for your application performance. For example, users don't tolerate slow connections. This type of monitoring requires a different approach than alerting on errors in one of the layers in your stack. Amazon CloudWatch collects monitoring and operational data in the form of logs, metrics, and events. With CloudWatch, you can get a unified view of AWS resources, applications, and services. Review logs as a flow of events ordered by time. Query log data interactively with CloudWatch Logs Insights. Use default operational metrics from AWS services. and configure alarms based on metric thresholds and initiate automated actions. Lambda logs all requests and results in a CloudWatch log group called /AWS/Lambda/function name. A one-to-one relationship exists between function and log group. The first time that the function runs, the group is created. If you set up provisioned concurrency, the log group is created when you create the provisioned concurrency. The log group is the entity that you would typically use for searching events within your Lambda logs. The log group is made up of log streams, which are identified by the date, function version, and a unique identifier. Lambda automatically creates new log streams within a group. They are based on internal factors that are related to how invocations are allocated to environments and the timing of invocations. When you test functions from the Lambda console, log information is presented to assist with debugging. The console highlights the success or failure of the invocation and provides summary information from the log entries. Each log stream contains a sequence of events that describe Lambda request details. Each request includes a unique request ID and a start event, end event, and report event, which quickly tell you summary information about the Lambda request. The request ID is the primary identifier that you will use to find events related to a particular invocation. The report event is a quick way to see how long the function ran. It also shows the billing duration, the memory that is configured for the function, and the memory that it used. AWS X-Ray traces requests that travel through your application and shows a map of your application's underlying components. X-Ray has the following features: one-click enablement for Lambda functions and integration with other AWS services, an X-Ray SDK to capture metadata for API calls that are made to AWS services with the AWS SDK, visual detection of latency distribution and quick isolation of outliers and trends, easier debugging of application code, and filtering and grouping of requests by error type. An X-Ray trace contains a few parts. The first is a segment. A segment provides the resource's name, details about the request, and details about the work that is done. A segment can break down the data about the work into subsegments. Subsegments provide more granular timing information and details about the downstream calls that your application made to fulfill the original request. A subsegment can contain additional details about a call to an AWS service, external HTTP API, or SQL database. You can even define arbitrary subsegments to instrument specific functions or lines of code in your application. Annotations include key value pairs that can be indexed and used with filter expressions to group traces in the console for easier analysis. And metadata includes key value pairs of any type that are not indexed but can be used to store data in the trace that you won't use for searching traces. This slide illustrates an X-Ray trace that is generated when an API created by API Gateway invokes a Lambda function. Here are the key takeaways for this section of the module. Modern applications require more than traditional operations monitoring. CloudWatch provides built-in logging and metrics to monitor your Lambda functions. With X-Ray, you can trace requests across your application to find trouble spots quickly. Thanks for watching. We'll see you in the next video.
Welcome to Module 8, Introducing Containers and Container Services. Section 1, Introduction. At the end of this module, you should be able to describe the history, technology, and terminology behind containers, differentiate containers from bare metal servers and virtual machines, also known as VMs, and illustrate the components of Docker and how they interact. You should also be able to identify the characteristics of a microservices architecture, recognize the drivers for using container orchestration services and the AWS services that you can use for container management, host a dynamic website by using Docker containers, and describe how AWS Elastic Beanstalk is used to deploy containers. In this module, you will learn about containers, Docker containers, using containers for microservices, AWS container services, and deploying applications with Elastic Beanstalk. Frank and Martha recently acquired a coffee bean supplier, and they would like to include the supplier's inventory tracking system into the cafe's application infrastructure. Sophia is thinking about migrating the application database to containers to complete the integration.